Does it show your head? I don't think so.
I'm visiting GMU next week.
What's that?
I'm visiting GMU next week.
Oh, okay.
Why did I get this back plan?
That's not, I wasn't handing it back. Yeah. Is that yours? Or you're still?
But I need to organize it.
Oh, okay, fine. Yes, Ernesto was, he was completing his homework, this year, so it's all good. All right. Let me begin here with some verses, if I can find them again. So I'm reading from Philippians chapter 2. Where was I? Verse 14. Do all things without grumbling or disputing, so that you will prove yourselves to be blameless and innocent children of God, above reproach, in the midst of a crooked and perverse generation, among whom you appear as lights in the world, holding fast to the word of life, so that in the day of Christ I will have reason to glory, because I did not run in vain, nor toil in vain. So, I know, I have trouble with this, doing everything without grumbling or complaining. It's not in my nature, But anyway, I'll begin with a word of prayer. Heavenly Father, we thank you for this day and this opportunity we have just to meet and study your creation. Help us to understand a little bit more about tangent spaces today, Lord. In your name I pray, Lord Jesus. Amen. All right, so very much in John Lee's book, chapter 3, which is on tangent space. And I'll try to follow his book pretty closely. Tangent space. And so what he does, it's pretty neat. He begins by just talking about like geometric tangent vectors, all right? So in other words, if you can picture x1, x2, x3, xn, oops, my bad. I got to get my indices up here. Me slipping. Then you can imagine, picking a point, right, like A, and then you can imagine just attaching vectors to that, right? Like imagine attaching vectors at that point, and so we maybe put a little v sub A to indicate that the vector is attached to the point A, right? And so he points out, okay, so you could think of it specifically. You could denote it like A comma V to say, okay, that's the base point and that's actually the vector, right? You could use that technique to identify the base point of the vector if you wanted, but a nicer notation is just probably this V sub A. It's V at the point A. How do you add them? So, like basically, here's his notation. Rn sub A is equal to V sub A. All right, such that, A comma V with, I don't know how to write this other than say this, with V an element of Rn, right? I mean, that's essentially it. A is fixed through this discussion, right? A is fixed. It's the point at which all the vectors are living. And in this context, you can add vectors like VA plus WA is equal to V plus W sub A, and C times VA is equal to CV A. If you don't think I'm saying anything, I think to me, if we're going to get into this, fine, here's what I would, really we're doing like V comma, excuse me, my bad. A comma V plus, A comma W, how do you add those in this world? And I would sometimes, when I'm doing this, if I really want to be pedantic about it, I'll put a little sub A here, because it's not the standard vector addition, it's the addition at the point A of these vectors, and so it's A comma V plus W, right? And over here, C times, and it's really not just scalar multiplication, it's scalar multiplication at A, right? It's A comma CV, We're defining non-standard addition and non-standard scalar multiplication that's basically replicating vector addition and scalar multiplication at a point. Yeah?
Couldn't this all be shifted back to 0?
It could be, but we don't want to.
Yeah, 'cause we want to do it
So,
on manifolds.
right, I mean, in physics, essentially, we're working in physics, and a lot of times in applied mathematics, we work with the equivalence relation, right? We work with basically AV is equivalent to, BV, if and only if what? Well, BW. If and only if V equals to W, right? So basically, two vectors at two different points are equal only if they have the same, attached vector at the point. But in typical applications, you're right, we just shift back to the origin, and this is the game we play in physics and so forth. But we'd like to distinguish vectors at different points now. So that's this contraption here, V and RNA. And so furthermore, we've got EI A is, I equals to 1, 2, n is basis for RNA, all right? So these are the usual standard basis, but attached to A, all right? So that's yet another notation. We use this VA. Also, sometimes he'll write as V bar A, okay? In this context, great. All right, so it's easy enough to verify that this is a vector space, right? And you can literally see how that would just be what we would think of as the classical tangent space to a embedded submanifold in Rn, right? You just take all of these vectors which sort of kiss the surface at the point and appear as tangent vectors to actual curves in the surface, right? Something like this, yeah.
When you say base an element of Rn, do you actually mean that both A and B are elements of Rn? We're basically just adding them together? Or
No, I mean V is an element of Rn. Here, A is also an element of Rn, true.
yes.
But it's fixed throughout this discussion. Yeah. And, you could think about something like a sphere, pick a point, right? And then you could imagine all the curves that go through that point, right? And you could think about all the tangent vectors to those curves at that point of attachment, right? And, you could think about then, there's literally some kind of, plane here, which you could think of as, so that, like the tangent space here would be like a subspace, right, of R, in this case, I'm talking about a sphere in 3 dimensions just for the sake of discussion here, so like R3P, it would be a particular subspace of R3P, which we could visualize as being attached to the sphere at that point. That would be the tangent space. That would be the sort of most concrete, natural notion of tangent space, right? Even if I wasn't, set aside manifold theory, that's what I would teach in an advanced calculus class, for example, where I'm not being abstract. That's the concrete tangent space, right? And of course, you could also do that in Rn. But then, if you had a k-dimensional submanifold of Rn, you'd have like a k-dimensional tangent space, something like that. All right. Let me get back to John Lee's book. I think that's just, kind of a natural jumping off point. Okay, so then let's get weird. So he says, the only things we have to work with on smooth manifolds, though, so far are smooth functions, smooth maps, smooth coordinate charts, right? So this isn't going to work in the abstract, right? Because we want to think of a manifold as sort of an abstract set. We don't want to necessarily, at the start of everything, think of it as a subset of Rn, right? There are apparently some popular books that do this, but like I was talking to my student who's at a other place, and he's saying the book they're using actually does that. He's like, it's just horrible. But anyway, so we're not going to do that. We want to think of our manifolds abstractly, at least to start with, all right? Okay, so how do we do that? So he says, for any example, any geometric tangent vector, VA, yields a map as follows. So we can, here's a correspondence. We can take VA in RNA, and it will correspond to a map, let's call it D sub V A, which is a mapping from smooth functions on Rn to R. All right. And what is this? What specifically? How do we define this this map on smooth functions to R? All right. How is that done exactly? All right. So that's the directional derivative. It's really the directional derivative in the sense of advanced calculus. It's not the directional derivative in the sense of calculus 3 because we're not assuming that V is a unit vector, as we often do in Calc 3. So this is the grown-up directional derivative. And here's how it's defined. So d v sub a acting on f is equal to d sub v f of a, which in particular means take the time derivative at t equals to 0, evaluate, basically this means differentiate, then put t equal to 0 at the end, all right? That's what that means. F of what? A plus tv. So this is a definition, all right? So you see, given a geometric tangent vector, we can define a corresponding differential operator. All right? So the differential operator is simply obtained in words by composing the function that you're given with the line which has direction vector v and is based at a for t equal to 0. All right? It's very natural. And that is exactly what the directional derivative is. It's just we insist on unit vectors in Calc 3 for the sake of it having an unambiguous interpretation in terms of min-maxing. Okay. This still has lots of information about, minimums and maximums, increasing and decreasing for the function along the direction. It's just that its magnitude isn't particularly meaningful because you could rescale v. In particular, we have the following properties. dva of fg is equal to f of a dva, I'm still getting used to this notation, g plus g of a dv at a of f. Right? And before that, also dv, I really should write this one first, but if you've got a constant times f plus g, well, that's equal to the constant times dv at a of f plus dv at a of g. So it's linear, and it satisfies the product rule. All right? If you have a linear transformation which also satisfies the product rule, it's said to be a derivation. So a derivation is something that behaves like a derivative, but formally speaking, that's a derivation. Okay, so directional derivatives define a derivation on the set of smooth functions on Rn. All right, so, and he says, if you want to be more concrete here, you should notice that we can in fact write dv a of f equal to vi partial f partial xi of a. If I could just kind of drop back to Calc 3 notation for just a sec. What is this in Calc 3, the notation? Something like the directional derivative of f in the v direction at the point A, I'll write the formula gradient of f at the point A, dot product with v, you know? That's what this is, right? And the fact that that can be expanded in terms of partial derivatives of f is nothing more than the chain rule for Rn, functions from Rn to R. Okay, so let's see here. And so what's a particular case here? If we put, what happens if we put v equal to, if you put v equals to the standard basis, what do you get here, by the way? What's the directional derivative in the, you know, yeah, oh man, horrible notation, look at this. Oh, I'll just say v, in this case. v a of f, what's that equal to? Well, it's just equal to partial f, partial xi at a, all right? All right, fine. Let me get on with it here. We need to make a definition. So if we, if A is a point in Rn, and W is a mapping from C infinity Rn, oh man, to R, so a smooth function. Excuse me, that's not a smooth function, right? Well, this is a mapping from smooth functions to the reals. It's called a derivation at A if W is linear and satisfies the Leibniz rule. In particular, WFG is equal to f of A, W of G, plus W of F. Well, I guess he writes the G of A first. Fine, G of A. These are real real numbers, so they commute. Like you could write them in either order. It doesn't really matter, right? But there it is. So it's linear, and it satisfies the product rule or the Leibniz rule. That was what we said. That makes it a derivation. All right. Now derivations are going to be what we primarily take to be our tangent space in this course. Our primary view of what a tangent space is to a manifold is going to be a set of derivations. That's why we're doing this. Because it turns out that is as he explains at the end of the chapter, that's the nicest viewpoint because it has the advantage of not being an equivalence class thing. All right, derivation is a specific thing. It's not an equivalence class of things. And it nicely and concretely interacts with smooth functions on the manifold, which are really where the heart of the matter is. Like the set of smooth functions on the manifold in some sense describes the manifold itself. There's a homework problem at the end of chapter 3 I almost assigned to you, but I recanted, which really delves into that. So, all right, but I'm trying not to kill you guys with too many problems. So, all right, so that's the derivation, and the notation for this is just that W is an element of T, A, Rn. All right, so this right here is the tangent space. Tangent space to Rn at A. Okay. And he says, okay, so clearly it's a vector space under the operations. What operations? How is this a vector space? What do you mean it's a vector space? How do you? So let's see here. Why is it a vector space? So let V and W be derivations. Yeah. Then how about this? V plus W. If we let that act on F, what's it equal to? And how about C times V acting on F? What's that equal to? V and W are both functions. They're real valued functions of smooth functions, right? They're themselves mappings. So if we define them by this, then we've defined vector addition, because if you define these, pointwise defines the addition and scalar multiplication. And this is, of course, what? For all f that are smooth functions on Rn, right? So that makes that a vector space. He says the most important and perhaps surprising fact about the tangent space today to Rn in this way is that it's finite dimensional. So it's naturally isomorphic to the geometric tangent space that we just talked about at the start of lecture, right? And so let's work out his lemma 3.1. All of these building blocks are used as you go on. He bootstraps everything from this geometric derivation stuff on Rn. Everything we prove here, he lifts to the next stage. So it all folds together. It's really cool, the arguments. It's very slick. Lemma 3.1. Did I move the camera? Well, sorry. Person not here. Let's see here, properties of derivations. So A in Rn, W, a derivation, F and G, smooth functions. This marker has not long to live. Let's see if it'll make it through this thing. Maybe. If F is constant, then WF equals to 0. B, if f of a equals to g of a equals to 0, then W of fg equals to 0. All right, you're done. Oh man, that was right in the trash can, just like I planned. Okay. All right, so proof. And the proof does touch on some things that I haven't emphasized too much in here. So he says it suffices to prove A for the constant function. So like if we have f1 of x identically equal to 1, right? Then notice that f of x identically equal to c has what? You've got WF equals to W of CF1, right? That's the formula. If F1 is the identity identically equal to 1, the identically constant function is just F1 times C times F1, like that, right? And so that is equal to C times WF1, right? And so if we can prove that this is equal to 0, right? So if we can prove that this is equal to 0, then we've got an arbitrary constant is equal to 0. So it remains to prove that WF1 is equal to 0. All right? For F1, that's easy though, right? For F1, notice F1 is equal to F1. And here I don't mean composition, I mean like product. Okay, so then has what? We have W of F1 is equal to W of F1, but this tells me what? It tells me F1 of A, W of F1, plus F1 of A times W of F1 equals to W of F1. But what is F1 of A? F1 of anything is 1. So what this tells me is that 2 times WF1 is equal to WF1, which is a fancy way of telling us that WF1 is equal to 0, which at this point, we go back up into here, and we're done. Okay, so that's the proof of A. And that is a mighty fine test question, isn't it? I mean, that's not, if I was teaching this in a more formal sense, that'd be a nice test question. Okay, so, all right, so then B, how do we do B? Just look at W, let's just calculate it. What's W of Fg? By the product rule, that's F of A, W of G, right? Plus G of A, W of F. But by assumption, that is 0, therefore this is a 0. All right? There you go. Then proposition 3.2, it says that for A in Rn, all right, A, for each VA in the geometric tangent vectors based at A, the map dV at A from smooth functions on Rn to R defined by 3.1 is a derivation. Okay, in other words, dV at A is an element of the TARN, all right? In short, that's what he's saying. The directional derivative is, in fact, as we've claimed, an honest-to-goodness derivation. And what more? What more than that is true? Well, what more is true? 3.1 is that boxed equation from the first board, guys. Part B is that the map VA maps to the directional derivative at V, at A in the V direction, is an isomorphism. From the geometric tangent vectors based at A onto the derivations based at A. All right. So part A is actually pretty much obvious from the definition, which I'll write again over here. So for part A, from part A, what was our definition? Well, dV at A acting on F is what is equal to what? It's equal to, if you'll allow me to just drop back to calculus 3 notation for a second, just to make it sort of glaringly obvious what's going on here, it's the gradient of F, right, at the point A, dotted with V as a vector. So fun fact, the gradient of F times G is equal to, F times the gradient of G plus, G times the gradient of F. You can prove that for gradient. It's not hard. It follows from the product rule for each partial derivative at each component. So the product rule applied each component one at a time gives you that. And then evaluated A, that's the product rule for the directional derivative. Linearity, well, linearity just stems from the fact that the gradient of F plus G is what? That. So essentially these two identities, when you put them up to here and sort through how we've defined the directional derivative at A, they give us A. So how about part B? It's an isomorphism. So let me just be clear. I'm going to invent a letter here. psi of VA is equal to dV at A, right? I want to show that that map is linear and bijective, right? Okay, so linearity. So what if I had like psi of VA plus WA? How would that go? So that would be, by definition, d of V plus W at A, right? And so to understand that, I have to let it do what? I have to let it act on a function, right? Let it act on a function, because that's what they do. So then I have d of V plus W at A acting on a function. But that is nothing more than the gradient of f at the point A dotted with V plus W, which, by the way, is the gradient of f at A dotted with V plus the gradient of f at A dotted with W, which, by the way, is the directional derivative at V at A acting on f plus the directional derivative of V at A acting on W on A acting on f, right? Which is dV, which in short is psi of VA plus psi of WA acting on f. But this holds for all f, therefore psi is in fact a linear map. Okay? So it's linear. How about injective? What happens if we, suppose that psi of VA is, is equal to 0? What's that look like? Well, that's saying that the directional derivative in the V direction at A of f is equal to 0. In other words, the gradient of f evaluated at A dot product with V is equal to 0 for all f, for all smooth functions, right? And what does that tell you?
Kernel 0.
Why? Why does this imply that f has to be 0? Or V has to be 0 is really what I'm interested. My goal is to show that VA must be by necessity 0. I have complete freedom to use any functions I want. Which function should I use to extract information from here? Like, what makes this the standard basis? Right? The gradient of the xi coordinate function is EI. Right? Like the gradient of x1 is 1, 0, 0, 0, 0. The gradient of xn is 0, 0, 0, 0, 1. So if I use that f, then this becomes EI dot V, right? Which, gives me V sub I equals to 0 for all I. My index placement has gotten a little askew here. My apologies about that. I'm not sure where I've brought in this transgression from. It's probably my use of Calc 3. Lee is careful to not really show these details. He just claims what happens. And he claims it in the proper notation because he's smarter than I am. And anyway, long story short, VA is equal to 0, right? Therefore, the kernel of psi is equal to 0, which implies that psi is 1 to 1. Right? It's injective because we have this theorem in linear algebra. A linear map with 0 kernel is necessarily 1 to 1. That's a group theory thing, right? Okay, so then what? We just need to prove on to. How hard can that be, right? How hard can it be to prove on to? It's probably easy, right? What do you think? How's that going to go for us? you may recall at some point in my jibber-jabbering, I had mentioned that this use of derivations to codify the tangent space only works in the smooth category. In other words, the functions that we're dealing with have to have as many partial derivatives as we desire, and they all have to be continuous. Yeah, I gotta move it. Like to move it. Move it. Beep, 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 beep. All right, there we go. This is this is where that comes into play, the onto proof, because well, let's see how it goes. I think the proof here, it's pretty accessible. It's not too bad, but it is a little bit technical. And so here's how it goes. So we're trying to prove that psi, which went from where was it? Forgot my psi. Psi is not in Lee's book. This is what I made up. I give it a name.
RNA.
From where?
From RNA to VA.
Oh yeah, I never actually said that, did I? So yeah, from.
You kind of said, here's a new letter.
Yeah, so this goes from RNA to the tangent space at A of Rn. All right. Okay, so we'd like to prove that this is surjective. So to prove something surjective, we begin by saying let W sub A, well maybe just W. Let's just let W be an element of, the tangent space at A at Rn, right? And he says, define V to be VIEI, blah, 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 blah. All right, so let VI equals to W acting on XI, right? So that makes sense because W is a derivation. It can act on the coordinate functions. There you go. And define, we're going to define V equal to VIEI. All right. And that is, I think he wants to say, actually that's at A to be more fussy, that's an element of our RNA. And I think the claim is going to be that, what's the claim? The claim is that psi of this V, right, is equal to W. Okay? And, right, yeah, he says we will show that W is equal to, in other words, we can show, allegedly, that W is equal to the directional derivative in the V direction at A. All right, great. Now here's where it gets interesting. F of x, a smooth function, it can be written as f of A plus the sum I equals 1 to n of partial f partial x upper I at the point A times x upper I minus a upper I. All right. So far we're just staring at the linearization, right? The multivariate linearization of a function from Rn to R. Fine. And then there's this piece, plus. So here he's appealing to Taylor's theorem, which you have never before seen nor proved, but I'm going to allow it. So x upper I minus a upper I, x upper j minus a upper j. I found a sort of self-contained proof of this in the book Differential Manifolds by Lawrence Conlon, but that proof is a little bit harder than this, I think. Although I do think there is a proof of this in Appendix C, maybe. I haven't had a chance to look at that. And we do have many things to cover, so I'm probably going to let it go. You know, there you go. So this is a formula which is known for a smooth function that relates the smooth function to its derivatives at the point in question A. And this is Taylor's theorem. Taylor's theorem only applies in this sense if we know that f is smooth. I think that this theorem breaks down if f is not smooth. This is the problem. Okay. So anyway, check it out. If you look at this expression, what happens if we, you know, hit w on this thing? Like what's w of f equal to?
Hey, Jack.
Okay. So w of f, right? It's w of all of this. But some really cool stuff happens, right? Check it out. This right here, if you think of it, let's think of this as like G1 of x. Let's think of this as like a G2 of x for the sake of discussion. What happens when you plug in a into those? It's 0, right? That happens for every I. So if we go back to the lemma 3.1, remember that if we have two functions that evaluate to 0 and a derivation hits them, 0. So, I mean, really, I mean, okay, fine. We could maybe we should think of maybe I have to include all of this into that too, but basically the point is that I think maybe I should include, I don't know, you can lump all of this in as well into the function, you know. The point is, if you let w hit that, every time you've got a product of two things that both are 0, right? And they're both by assumption smooth, so it's within the context. Long story short, this piece is 0 when w hits it. And so what are you left with? Well, you got yourself a w of f of a, right? Plus the sum I equals 1 to n of w. Well, let me just get to the point here. This is a constant, right? So I can pull that out. And then w hits, well, you got w of xi minus w of ai. I'm going ahead and using the properties of the derivation, yeah?
And isn't that 0?
Ah, yes, very good. And then so half of this, a lot of this stuff is 0, right? 0 because f of a is a constant. 0 because a component is still a constant, right? It's also a constant. And yeah. And what's this? That by definition is your v upper I. Well, I mean, you could, anyway, that's vi as we defined it, right? And so what you got is you got a sum I equals 1 to n of vi partial f partial xi at a. What were we trying to prove?
Surjection.
Surjection.
Claim at the top right.
Yeah.
Trying to show that the weight is
Mm-hmm. Okay, so I guess to finish it, if you like, if it's not already obvious, maybe it's not. If we just think about, again, do that trick again, all right? Let f equals to x upper j, then w of x upper j is equal to what? The sum I equals, oh, really? We're far too close to the facts department. All right. Anyway, what I'm trying to get at here is that oh man, I've just lost my way. I'm sorry, guys. There's nothing more to do. So this is literally d sub v of a acting on f, which is what we're trying to prove. Let me not make it more complicated than it actually is. Duh. So anyway. All right, there you go. So what? So now that we've proved the set of derivations, smooth functions on our Rn is finite dimensional, we'll be able to use that to capitalize on the fact that that's still true on a smooth manifold. All right. So how do you define the tangent space on a smooth manifold? What's our definition for the tangent space on a smooth manifold? What should T, what's TPM going to mean if M is a manifold? Yeah, what's this thing going to be? If M is a manifold, not, you know, we're not in Rn now. Now we're actually, you know, talking about a smooth manifold here. How should I define the tangent space at a point to the smooth manifold? So it's going to be, you know, V such that you have smooth functions on the manifold. It maps smooth functions on the manifold to the reals such that, you know, V is linear and V of Fg is equal to F of P Vg plus G of P Vf. In other words, the tangent space at a point P on the manifold is going to be the set of derivations on the smooth functions of the manifold. Same definition as T sub A Rn. Okay? So not at odds, same definition. And so what are the lemma? If you've got a smooth manifold with or without boundary, and you've got a point on the manifold, and, you know, for P and M, V in the tangent space at P to M, and F and G smooth functions on M, all right? Then part A, if F constant, part B, if F of P equals to G of P equals to 0, then what? Then what? Then V of F is equal to 0, and V of Fg is equal to 0. Okay? Fortunately, I don't have to prove that because that's your job. I said it's one of the homeworks on mission 2, but I expect that the proof is similar to the one I gave you today, except that, well, anyway, there's some things to think about. All right, so that's that. Next up, definition. If suppose we have M and N smooth manifolds, all right, with or without boundary, all right, and you've got F, a smooth map from M to N, then we define df sub p, the differential of f at p, as a mapping from the tangent space at p to m to the tangent space at f of p to n. This is called the differential of f at p. All right. And the way we define it is as follows. For v in the tangent space at p to m, and f a smooth function on n, here's how it goes. D fp of v, that acts on f according to v acting on the composition of little f with big F. Now I kind of don't like this. I'm gonna opt out of f. I'm gonna put a g in here because I just like it. I like it to look different. I want to have a g and I want to have an f. So my function on n is going to be g, and my smooth function is going to be big F. All right, so then no two F's here. Let me sort through that this makes sense, okay? So like, think about this. Let me draw a picture. I'll put a hole in for once. There you go. Check it out. I put a hole in the manifold. Happy? M, he's always putting holes in his. I feel like I'm always giving you guys boring manifolds with no holes in them, kind of depriving you of like half of the experience. Are you happy? It's better? No. I don't know. So M, N, F. Let's see here. G, where's G? G is a function. So I think of it this way. G is a smooth function from N to R, right? So how about this G composed with F? Where's that guy? That's this, right? G composed with F is here. See how it goes? You take a point here, and then it goes, am I on the right board? I'm like, did I ever shift over to the middle board? I feel like an idiot if I'm pointing at where I'm not writing. Okay, I'm still an idiot, but pointing in the right place. Let's see here. So here, over to here, and then G goes down here. And so in short, G composed with F is actually a what? This is straight up an element of C infinity M, right? This is a smooth function from M. What is V? V is a tangent vector to M. What does it do? It's a derivation on smooth functions, right? So this makes sense. This V is acting on what it ought to, which is a smooth function on M. Let me go through a short little calculation with you guys here.
Have to be smooth.
Yes. So yeah, let's see that it's in fact a derivation, right? We do need that. So the differential at P acting on V, let's let it act on a function F and G, multiplication, right? So by definition, put this piece of paper down here. And sorry, I've got two F's again. It's just going to happen. So by definition, this is what? This is that, right? So I got to have V acting on what? F times G composed with F, right? But we went through this the other day. When we have a product composed, it ends up being the product of the compositions. You see, so this is nothing more than V acting on F composed with big F times G composed with big F, right? But how does that work? Well, V is a derivation, right? So this is straight up going to give me, let's see here, Yeah, we're fine. F composed with big F of P, I believe, yeah, times V of G composed with F plus G composed with F of P times V acting on F composed with F. What's that? Let me write it out. How does that work? What are we looking at? We've got F of big F of P times V of G composed with F, right? Actually, let me get to the point here. So that's that, right? But what is this? Let me do more writing than I need to. What is that? By definition, that is D, right, you got it. D, F, that's the differential at P of F acting on V, eating G. And then over here, you've got G of F of P. G of F of P, all right? And then you got yourself a DFP of V acting on eating F, all right? This is the needed product rule at F of P in N. In other words, this shows us that DFP of V is in fact an element of the derivations at F of P on N. Okay? Now, that's half of it. What else should I show technically? You'll forgive me if I don't. But we should also, of course, prove that the differential is linear, right? Because to be a derivation, it should be linear and Leibniz. I've just showed you Leibniz. And, but here's a picture. What's going on, it's kind of like this, right? So here's P. You've got a V here. And then over here is F of P. And this guy is your differential. So we take V, and the differential pushes the vector, you could say, pushes the vector over to df sub P of V. Sometimes this is called the push forward because the differential of a map, a smooth map, it pushes vectors in the domain of the function to corresponding vectors in the codomain. Right? Now, as he says, sometimes it's dangerous to call it a push forward because push forward is something people sometimes reserve specifically only for the context of a vector field. What's a vector field? A vector field is going to be an attachment of a vector at each point, right, on the manifold. Right, and then you may push all of those forward at once, and that would be like the push forward. A push forward of a vector field is another vector field. So some people reserve the term push forward just for vector fields, whereas this is, you might say it's a push forward at a point. If you call it a push forward, I'm not going to be bothered. I've called it that in the past. There are reasons for quibbling over these things, but none of them are as important as just trying to understand the basic things here. So let me shut up. Any questions? All right, so let's go on. Now, there are properties of the differential. I guess I'll write them over here. Oh man, this class is not long enough.